Hey, how's it going, everyone? I just want to do a video on flat Earth. I was just watching some videos of Antonio Subirats. I've heard his name, but I, haven't watched any of his videos. And there's also a PhD in spectrophotometry who did an experiment recently. And all the people in flat Earth, to me, it's like it's cool. Everybody comes from their different perspective. Everybody has skills and talents, and even the people who quote unquote are not doing it for the right reasons, whatever the right reasons are, they're still putting energy towards finding out what the truth is of the shape of the Earth. And so to me, all energy is going to be working towards coming up with a unique solution. And so that's what I wanted to talk about, is this notion of a unique solution. And I think as more and more math people get into it, and I'm not saying they're not already, to me, math is has always been for some people, difficult. It's almost kind of like public speaking. It's almost like universal that, a lot of people just have sort of apprehension, aversion, not a natural sort of inclination towards mathematics. And, I would say for me, I would say I'm above average, but the kind of people that I've been around in grad school, and realized quickly I was not at their level where they're writing 2, 3, 4, 5 pages of proofs. And a lot of times I've seen that you can get a PhD from great schools in mathematics, proving one thing, and that will take you 40 pages to prove and then explain what you did with rigor. And so that level of math is, to me, to give it an analogy in the languages, it's like someone who's extremely well versed in English, the English language, has great command of all the words, and their history, how they're constructed, spelling, and just writing, interpreting, all that kind of stuff, very comprehensive, very deep understanding of the English language. Whereas for me, I'm above average. I obviously know how to read, write, and speak, in English and stuff, and communicate with people, but not someone who's gone very deep into the English language, knows its origins, its history, and all that kind of stuff. That to me is like a mathematician, just someone who, because in math, that's the way that math people speak to each other, is through mathematics. And so that's their way that they express things that are going on in their brain to other people. And so it's not always easy or impossible even for some of us to comprehend that level of detail and rigor. I remember I took a real analysis class, and I only went to the first couple till I realized it wasn't for me at Rice. And the professor started off with what is a real number? And that's what math people think of. It's that's why the term PhD has an element of philosophy in it, because they're really starting from very, very first principles. And to me, that is the purpose of mathematics, is to express everything from first principles, from its very elemental level, and characterize it with equations. And the world that we live in, we have the ability to do that for a lot of things. And so mathematics to me is the depth and the understanding that certain people have is just their ability and their grasp to be able to articulate certain truths and then prove it using mathematics in a rigorous way, and proving that exclusivity as well, which are very important concepts, because solutions to mathematical equations and proofs require a lot of times exclusivity, that there are no other options, that this is the solution to this, or being able to characterize what all the solutions are is another great mathematical accomplishment. So there's different objectives when using mathematics, but it's always concise. It's not like philosophy in other aspects of it, or religion, and stuff like that, where it's open-ended. There's interpretation, there's faith, and all that. To me, mathematics is the opposite. And it makes it different than fields like physics, and even chemistry. Where there is sort of uncertainty and ambiguity about certain things, and that's okay. That it's open for future discovery, or it may never be able to be discovered. And even in computer science, it's okay for things to be ambiguous. With like quantization and just all that kind of stuff. And and I was thinking about one other example. But just basically every other field, there can be. I was thinking of accounting. Even in accounting, it's like rounding off and certain things, numerical precision and all that. It's accepted. It can still serve a very important function, but mathematics, and especially proofs and all that, usually require or is most valuable when there's uniqueness, or there's a very crisp understanding, in order to apply it and to use it in a useful way. And so it is kind of the language of logic, in my opinion, and people know it to varying levels. So, but I wanted to give just my quick take on this notion of uniqueness, and relate it a little bit to information theory and algebra and stuff. But basically, the way I see what's happening on both sides, and it's not a shot to either people. It's like, just again, like, I think enthusiasm on the ball earth and the flat earth side, whatever it is, whatever's motivating it, it's going to lead to a unique solution. It just, to me, it's inevitable. And in particular with the technology and stuff that we have available to us. And so I obviously feel the elite know, and it's their job to sort of allow it to get out in very, sort of in very sort of structured way. It is coming out and seeping out, but God does not want this to happen with kind of one home run sort of thing. And to me, if it were that way, it would be very, very overwhelming for both sides, really, at this point, whatever the truth is. But this notion of like uniqueness, basically what's happening right now are observations. It's like certain things that people are doing, like ball earthers, and in particular reds, will use like the sun, staying the same size after applying solar filter, I guess, aggressively enough. And then they'll be like, that's impossible on a flat earth. And then flat earth people will look at certain observations and say, well, that's impossible on a ball earth. But the actual truth is that it's impossible on a ball earth with that radius. And then the same understanding needs to be applied with Red's observation, is that it's not rigorous, first of all, that he knows that the sun is not changing size unless it's measured very, very precisely. And then if that were the case, that does not necessarily imply that that the Earth is a ball. It could just mean that the radius of the Earth is a lot different than what is modeled. It could just be a massively big ball that's very, very close to flat over the duration of that observation. And so, all these things are possible. So on both sides, you're not completely disproving one or the other. You're just disproving the parameters that that observation is contrary to. And so that's the main point that I want to make, is that all these things are observations. And in algebra, if you have a system of n equations, you need n linearly independent equations to solve that system of n equations uniquely. And so if you don't have that, if you have any number less than n, you will have an underdetermined system. And so the solution is not unique, which means that you can fit an infinite number of variables through that, and still get the correct answer. You'll still be able to solve that system of equations. It's not that it doesn't have a solution. It's just that there will just be an infinite number of them. And so only when you have n independent equations, linearly independent equations, will you get a solution of n unique values. And so that's a very important concept, because if we think of those n linearly independent equations, those are n linearly independent observations in the case of ball Earth versus flat Earth that will allow a person to have comfort that rigorously those parameters are unique. And so you would need many of them, because we're dealing with a multivariable solution, because we have, in this case, like the size of the sun, the distance to the sun, the radius of the Earth, and the distance of the Earth to all these different objects, and all that kind of stuff, and so and with the observing things in a distance, we have different sizes and perspective, and refraction, and all these things that are potentially nonlinear add to the complexity of this. And so just using the simplified example, with n linearly independent equations, you need quite a few of observations, and they can't just be reinforcing one another, which is what the notion of linearly independence means. Is that if you have two linearly dependent equations, and if you think of just vectors for now, two linearly dependent vectors are basically collinear. Like they will be lying on top of each other, and so they're basically like just stretched versions of one another, or they're parallel. And so that means that if you think of this like graphically or visually, if you have two vectors that are non-intersecting or parallel, they will never intersect, so they will not have a unique solution, which essentially means that they're kind of telling you the same thing, that they are essentially mathematically, from solving a system of equations perspective, they're telling you the exact same information, even though they happen to be in a different place in space. And when they're lying on top of each other, they might just be scaled versions of one another, but they are also not telling you anything new, because they are essentially the same thing. They're mathematically identical because they're lying right on top of each other, and so any solution to one will function as a solution to the other. And so those examples are what are known as linearly dependent. We could think of them, they're basically just dependent on each other. They are mathematically, like I said, the same. So linearly independent, and the best form of linearly independent is if you have vectors that are orthogonal, or if you think of like two-dimensional space, 90 degrees apart. And so, those are kind of the most sort of uncorrelated. They're the most dependent on one another. And so they are kind of, for mathematical terms, the strongest version of an observation. It would be like an observation made, on the moon, and an observation made on the sun, and not having to be dependent on each other because they're functioning independently. And so, as opposed to like two observations about the sun that actually maybe just reinforce one another. So the more number of independent observations, like one related to the moon, one related to the sun, one related to an object in the distance, something related to the stars, something related to anything else related to like curvature or water, or anything that, the more and more things that are just independent, like weather patterns, or like tides, all these different sort of angles that people are coming at for quote unquote proofs. The more of those that are stacked on top of each other and are not dependent on one another, or very loosely, maybe not perfectly 90 degrees, but not, the same thing. The more of those that you have, eventually you'll be able to produce a unique solution and say, not only is the shape of the Earth this, but it will have these characteristics, like this radius, this distance to the sun, moon, and all that kind of stuff. And so it's very much a multivariable solution. Like just it's it's many, because we're dealing with an Earth, and the sun and the moon presumably would be part of these observations and the solution, because we would need to know that, because those are things that we can actually see and observe and measure. And then so just that alone, we're dealing with the size of 3 different things, and then the distances between all of them. That alone, will get us to like over 5 to 10 variables right off the bat. And then there's still a lot of other things beyond that we would need to be able to characterize and explain to be able to ensure that we have a unique solution. So to me, all these different things, and I see on the flat Earth debate with Nathan Oakley, he's careful to like check people and say this is not a proof, this is just an observation, and it is, but enough observations, and we're dealing with a structure that we know that it's kind of immediately not certain things, like it's we know it's not like a cube or anything like that with corners and stuff like that, like there's certain shapes that we can eliminate. So that to me helps in the search space of all the different possible solutions, that we know that it's going to be essentially some kind of radius. If we think of it like an infinite radius will be like a flat surface, or it's going to be some finite number, it's going to be some shape with like a radius, and if we, again, like I said, r equals infinity would be a flat surface, and so that helps, and so we can limit our search space to that, and then find out what that radius is if it exists. And so that to me is sort of the mathematical understanding. And I was asked on my first non sequitur debate about the notion of aliasing in signal processing or in electrical engineering communication systems. It's basically the fundamental of that is that if you undersample a signal, then you could potentially when you try and reconstruct it, you could confuse it for another signal. Like let's say you have a high frequency signal, but you don't sample it frequently enough, you could actually confuse it for a much lower frequency signal. And so you need to sample it at a certain rate, and that's what the Nyquist criteria states, that you have to sample a signal at least twice the maximum frequency in that signal, in its frequency spectrum, in order to ensure that you're not getting an alias signal, you're not getting ambiguity after you sample it. And so that's just similar to like this kind of thing too, where we're talking about a uniqueness of solution, is that you need to have enough observations to ensure that you have a unique solution. And so it holds in linear algebra, it has to hold in communication systems, and in many ways there's also a information theory kind of example, is that if you repeat the same thing over and over again, there is zero entropy in that, and there's zero information encoded in that signal. And so to me, if you take a vector and just stretch it, you're not adding any information. So in a way, you can think of it from an information theoretic perspective as well, that there's no new information that you've added by just stretching a vector. It's the same thing, and so it doesn't serve you any greater purpose to solve a system of n equations, to solve it uniquely. It could still serve a function, but it does not serve you getting towards a unique solution. And so there's aspects of that also in information theory. And so that to me is just something to keep in mind. It helps us on both sides be a bit more sober in terms of like saying like proof, because proof is like, I know it's, again, we're just like kind of going back and forth with them, and this is just a little bit more in the details, but to have something proven from a mathematical perspective rigorously, would require n observations, whatever those n observations are, that will ensure that the solution for the radius of the Earth and all those distances and all those observations come from a unique set of variables. In this case, there would be n, and there is no other solution to that. There is no other set of parameters that will work, that will get you all those observations. So until all the different things that we experience and notice and see can be characterized with a set of linearly independent equations, and it goes through the whole list of all the different observations that are possible, we cannot say that we have a unique solution. And so you can definitely say that there's strong evidence that there's more observations for one than the other, which gives it a higher probability of being true. But again, until we have characterized all the different observations with a set of n linearly independent equations and observations that characterize those observations, we do not have a unique solution to what the shape of the Earth is in detail in terms of all the numerical parameters. And so I just wanted to throw that out there and just use the analogy for linear algebra and the Nyquist criterion and all that kind of stuff, just to help us be, a bit more sober in terms of like thinking we've landed on something. But, to me, obviously, if you know my channel, I definitely, believe we live on a flat Earth. To me, it's a certainty for a lot of different reasons, not just the technical, but there is just a lot of things that literally to me are mathematically impossible on a ball Earth. Okay, hope everyone's doing well. Take care. Bye.